Lecture 9-4, Evidence about Earth's Past. Fossils are the remains of or trace of ancient organisms. They form because the material left behind by the organism gets replaced by minerals, which form into either just mineral formation or into a rock. Body fossils are any part of the body left behind, like, say, bones, teeth, something like that. Trace fossils, they're going to be something that shows evidence, so more like footprints, excrement, something like that. Now, fossilization is a very rare process, which is why of all the organisms that exist on the Earth, only a very, very small percentage are ever fossilized. And the reason why is because decay and predators remove many of the body parts. The soft parts are hardly ever preserved because instead of getting pressurized, they just decay. So special circumstances must be present for a fossil to form. You think about a lot of the fossils we find in Iowa, which are tiny little sea creatures. Well, a long time ago, that sea creature died on the bottom of a seabed. And so what happened was sediment fell on top of it over time, kind of preserving it. And over time, that would compress and get compressed some more. And then so mineralization would take place. And so the shell or the hard body parts would get replaced by minerals. And now we have something that is preserved in the rock layers. It's very, very difficult to have fossilization occur unless certain conditions are present. We will not find fossils for every organism. We have found footprints. We have found leaf impressions. We have found lots of bones, seashells. Hard stuff is going to fossilize much more easily than soft stuff. Now, index fossils are widespread fossils, organisms, but they only existed for a relatively short period of time. So I have this fossil I can find, like, say, in South America or Africa, but it only existed for, like, say, a couple 100,000 years. What that does is now it's a useful tool to identify when certain rock layers formed, when certain events happen. If I find this fossil in this layer of rock, I know when this fossil lived. I can tell when that rock layer was formed. We have opposites of index fossils called a living fossil. They are organisms that existed for a tremendously long period of time without changing very much. You can even look at modern-day sharks or alligators. These could almost be examples of living fossils because they have been around for a very long time without major changes. So we find them in the fossil record. They aren't very useful for identifying. Index fossils are very useful because I can find them, say, when the rock layer formed. Some of the fossils we have in our classroom, the little seashells, we know when those organisms existed, so I can look at the rock layer in which I found them and say, okay, this rock layer formed within a 100,000 year time period. Now, dating rocks, which not going to the movie, but how old rocks are. We can do done a couple different ways. The relative age, which gives us its age compared to other rocks. It won't tell us how old it is, but it'll say it's younger than this rock, older than that rock. Law of superposition is just in horizontal sedimentary rock layers. The oldest layer is at the bottom. Each higher layer is younger than the layers below it. So here you can see the oldest layers are at the bottom, the youngest are at the top, and of course soil and stuff is forming at the very top. And so each layer here, you can kind of see the little striations in the rock layers, and you can tell when rock layers form. So this would be newer, this would be older. And so relative age is just trying to figure out in the order events occurred. Is this rock layer older or younger than the other rock layers? In this example here, of course, the stuff on the top is going to be the newest. This is a little intrusion. So intrusion, we should remember that from previous sections. All of these rock layers around it had to be there in order for this to form. So this is younger than all of these rock layers. We can tell that this rock layer was probably the oldest. This formed on top of that, so it's a little younger, a little younger, a little younger, a little younger. This formed across layers, so this is younger than that. This is younger than that, so this is kind of like another intrusion. Then you can see the oldest layers are at the bottom, so this would be our very oldest layer, and the youngest layer is right up here. And so we can figure out from this when each layer formed. We can't tell how long ago, but just the order. So intrusions, magma cools, hardens, as forms previous layers of rock. Intrusion is always younger than the rock around them. So intrusion is always younger than that. Faults are always younger than the rocks they occur in. So if I find a fault line, that rock had to be there in order for the break to happen. So the fault is younger than that. Unconformity, that just means the surface where new rock layers meet a much older rock surface beneath them, where previous rock layers kind of get either worn away or pushed away. So unconformity is a gap in the geological record. We kind of like skipped it. It'd be like if we numbered things 1, 2, 3, 4, then all of a sudden we go to 7 and 8 and 9. Well, we missed 5 and 6. Something had to happen to form those layers, to cause those layers not to be present. Then, of course, we can use index fossils to help us identify, relatively when rock layers formed. Now, absolute age is actually looking at the absolute age of the rock. Now, we can come up with a number, give or take a certain amount. So I can say a rock, well, this rock is 100,000 years old, plus or minus 10,000 years. Now, I'm not going to tell you that this rock formed 100,000 years ago next Friday, but we can tell you how close we are and what little range there is. To determine the absolute age, there are different techniques we can use. The main one we use nowadays, though, is radioactive decay. Radioactive decay is when the atoms of one element break down to form atoms of another element. And there are atoms in nature which are unstable. They are radioactive. They're constantly breaking down and forming different ones. And this is a natural process, but it's a very useful one because if the atmosphere doesn't change a lot, we can use this to identify how old something is. The rate of decay of each radioactive element is constant, and we use what's called the half-life, which is just the time it takes for half the radioactive elements to decay. So like, let's say I have 100 of these atoms, the time it takes to go down to 50, that's its half-life, which would be the same amount of time it takes to go down to 25, which is the same time it takes to go down to around 12 and a half. Same to go to, and so we're kind of cutting in half each time. So the time it takes for half of something to decay, to break down and form a different element. Now, carbon dating is the one that you hear the most about. It is not the only radioactive technique that we use, but it works because there's carbon-12. And what this number represents is the total number of protons and the total number of neutrons inside of that atom. So this is the weight, or the mass of that atom. So carbon-12 has 12 total. Carbon-13, carbon-14 are the three main forms of carbon you ever find. So the only difference there is the number of neutrons that they have. The protons stay the same because protons tells you it's carbon. But carbon-12 has 6 neutrons, carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons because carbon always has 6 protons. So carbon-12 is most stable. 98.9% of all natural carbon is carbon-12. Carbon-13 is also stable. About 1.1% of all natural carbon is carbon-13. Carbon-14, there's a very, very tiny amount of this, but it's the one that's radioactive. What happens is that carbon-14 breaks down into something else over time. And we know how long it takes for it to break down. So the amount of carbon-14 in the atmosphere is relatively stable. In organisms, the amount decreases with time after it dies. So you and I have about the same amount of carbon-14 while we're alive. As soon as we die, since we're not taking in any more oxygen out of the atmosphere, the amount of carbon-14 in our bodies is going to start to decrease at a relatively constant rate. So we always compare the amount of carbon-14 to carbon-12 inside of an organism to estimate how long ago it died. Or in the case of rock layers, how long ago they formed. It can be identifying age of materials between 100 and 50,000 years old. So this is very useful for identifying like how old people are. We can't say that, oh, this person died 50 years ago, but I can tell if somebody died 100 or so years ago or thousands of years ago. Carbon dating is only really used for once living organisms because we need that carbon in there. We need something to kind of take in. And it can be used for things like plants, but most of the time it's useful for animals. Potassium argon is useful for 100,000 years to over 1 billion years old. Uranium lead is another type of radioactive decay. We can measure things from 1 million years old to 4.5 million years old. So I would not use uranium lead technique to identify something that died maybe 10,000 years ago or something that formed 10,000 years ago, but it'd be useful for finding something that formed more closely to when the Earth formed. So different materials are radioactive in nature. We can identify how much or a ratio in something compared to what we expect, and that can tell us how old it is or how long ago it died.